We are gathered here today because a mid-sized university is evaluating two proposals to install on-campus renewable energy systems as part of its sustainability initiative. The goal is to reduce the university's reliance on grid electricity and cut long-term energy costs. The university can either install a wind turbine on campus or set up a large solar panel array on its facilities. University administrators have limited capital and intend to choose either the wind project or the solar project. They have asked us to perform a financial analysis of both options and advise which investment is more viable. Please start for us, Jacob.
Hello everyone, welcome to our Group 15 case study presentation for ECON 137A, Manager Accounting with Professor Grover here at UCSB. I'm Jacob Carlos. Presenting with me today are Luke Dempsey, Brandon Conrad, Nolan Lawrence, Jeremy Patterson, and Zach William. The case we're working through is a wind versus solar energy investment decision for a university campus. The core question, given two renewable energy options, only one which could be selected, which one is a better capital investment and why? Here, what we will cover today, the fact pattern and case background, a step-by-step cash flow build, a year-by-year projection table, our NPV and IRR results, a full comparison, and a viability analysis across all 5 tasks, then all 5 discussion questions, and finally, our recommendations and strategy. Starting here with the fact pattern, a university is evaluating 2 mutually exclusive renewable energy investments, meaning only one can be chosen. Both projects sell electricity to the campus grid at 12 cents per kilowatt hour, and the university's required rate of return, the discount rate, is 8%. Project A is on the left, is the wind turbine. It requires a $2.5 million upfront investment. It runs for 20 years, it generates 6 million kilowatts per year, and has an annual O&M cost of $55,000. The depreciation base is $2.2 million. That's the $2.5 million cost minus the $300,000 salvage value. Depreciated, straight line over 20 years, giving us $110,000 per year in depreciation. Project B is on the right, is a solar panel installation. It's $1.4 million upfront, a 25-year life, a 2.4 million kilowatt hour per year, and an O&M cost of $22,000. The depreciation base is $1.5 million, investment minus salvage, giving us a $55,000 per year over 25 years. Those inputs drive everything we're about to show you. I'll pass it to Luke for the financial analysis.
So slide 3 shows exactly how we calculated the annual after-tax free cash flow for each project, step by step, following the capital budgeting method from Chapter 13. For wind, start with $720,000 in annual revenue, 6 million kilowatt hours times 12 cents. Subtract $55,000 in O&M and $110,000 depreciation. That gives us a taxable income of $555,000. After 25% tax, net income is $416,250. Then we add back the $110,000 depreciation because it's a non-cash charge to get the annual after-tax free cash flow of $526,255 for years 1 through 19. In year 20, we also received the $300,000 salvage value, bringing that finals year FCF for free cash flow up to $826,250. For solar, revenue is $288,000. Subtract $22,000 in O&M and $50,000 depreciation. Taxable income is $216,000. After-tax net income is $162,000. Add back depreciation, and we get an annual after-tax free cash flow of $212,000 for years 1 through 24, and $362,000 in years 25 when $150,000 salvage value comes in. So on slide 4, this is the year-by-year cash flow available for task 1. Rather than showing all 25 years individually, we're showing selected years that illustrate the key points, with the full model built in our Excel workbook. You can see that year 0 for wind is a negative $2.5 million initial investment. That's the cash outflow at the start. From year 1 onward, wind generates $526,250 in free cash flow each year. To find the present value of each cash flow, we multiply by the discount factor, which is 1 divided by 108 to the power of t. So year 1 gets a factor of 0.926. Year 5 gets 0.681, and so on. Each year's free cash flow times its discount factor gives us the present value of that cash flow. For solar on the right, same structure. Year 0 is the negative 1.4 million investment. Year 1 through 24 each generate 212,000 in free cash flow. The discount factors decrease each year as we get further into the future. That's the time value of money at work. Year 25 jumps to 362,000 because of the salvage value. The payback periods are also shown at the bottom. Wind pays back its initial initial investment in 4.75 years, just under 4 years and 9 months. Solar takes 6.6 years, about 6 years and 7 months. Wind recovers the investment significantly faster. And here are the full financial results, tasks 2 and 3. Summing all those discounted cash flows gives us the NPV for each project. Wind's NPV at 8% is $2,731,165. The IRR, which is the rate that the NPV equals 0, is 20.6%. That's more than 2.5 times the 8% hurdle rate. Solar's NPV is $884,699 with an IRR of 14.700. Both numbers are positive, both clear the hurdle rate, so both projects are individually acceptable on a screening basis. But these are mutually exclusive projects. The university picks one or the other. For preference decisions like this, the correct rule from Chapter 13 is to maximize NPV. Wind adds 1,846,000 more value than solar at the same 8% discount rate. Wind wins that comparison clearly, and I'll pass it to Brandon, who will walk through the full comparison, viability analysis, and the first 2 discussion questions.
Okay, thank you, Luke. So our first discussion question looks at how sensitive these projects are to electricity price assumption. In the base case, we assume the price of 12 cents per kilowatt hour, but it's important to ask what happens if electricity prices are lower. So starting with wind, every 1 cent drop in electricity price reduces annual after-tax cash flow by about $45,000. The main reason is scale. The wind system generates around 6 million kilowatt hours per year, so even a small change in price has a big impact in dollar terms. For solar, the effect is smaller but still meaningful. 1 cent decrease allows annual after-tax cash flow by about $18,000, which is roughly 40% of wind's exposure. That difference makes sense because solar produces about 2.4 million kilowatt hours annually, which is much less electricity overall. So if electricity price drops to 10 cents per kilowatt hour, wind's annual cash flow falls to roughly $376,000, but the project is still clearly profitable. At 8 cents, the economics start to get tighter. And at around 7.5 cents per kilowatt hour, the NPV of both projects is close to 0. So the break-even price of about 7.5 cents is roughly 37% below the 12 cent baseline. It's actually a pretty comfortable safety margin. In practical terms, it suggests the university should consider locking a power purchase agreement around 12 cents to protect itself from potential price volatility. So now let's talk about changes in project lifespan that could affect the results. In our model, the wind turbine is assumed to last 20 years, while the solar installation lasts 25 years. If the wind turbine only lasts 15 years instead of 20, the university would lose about $357,000 in present value. That represents 5 years of roughly $526,000 in annual cash flow, discounted back. Even with that loss, though, wind $2.7 million NPV is large enough to absorb the impact. For solar, the lifespan assumption matters a bit more, because its annual cash flow is smaller, about $212,000, removing the final 5 years, reduces the present value by $287,000. That ends up being a larger percent of solar's total NPV, which is about $885,000. There's also a real-world factor to consider with solar panels: performance over time degrading. So most commercial panels lose somewhere between 0.5 and 20% of output per year. Over a 25-year period, that could mean production in the later years is 10 to 50% lower than what we assume in the base case. On the other hand, there's also potential upside. Improvements in technology, stronger maintenance prices, or favorable operating conditions could extend the life of either project. And with long-term energy assets like these, even a few extra years of operation could add meaningful value. Overall, our base case assumptions are fairly conservative. And next, Nolan will talk about and walk through the risk, reliability, strategic considerations for the 2 options. Thanks.
Brandon. Discussion question 3 is on screen. It's asking which project has more predictable cash flows and how operational risk factors should influence the decision. Starting with output predictability. Solar has a clear advantage here. Solar irradiance follows fairly stable seasonal patterns, so you can forecast annual production with reasonable confidence. Wind is inherently more variable. Actual year-to-year output can deviate significantly from the 6 million kilowatt hour estimate, depending on weather patterns. That variability translates directly into cash flow uncertainty. From a mechanical standpoint, wind carries substantially higher operational risk. Turbines have hundreds of moving parts: gearboxes, generators, rotor blades, yaw systems, each one a potential failure point. Repairs are expensive and require specialist technicians that most university facility teams simply don't have on staff. Solar has no moving parts. Routine maintenance, cleaning, and periodic inverter replacement, something standard facility staffs can handle. The operational simplicity partially offsets wind's superior financial metrics and is a genuinely important consideration for a campus setting. Discussion question 4 is on screen. It's asking about qualitative and strategic factors beyond the numbers: visibility, space, permitting, maintenance, and scalability. On visibility, a wind turbine is a striking, highly visible sustainability symbol. It can attract donor interest and serve as a teaching asset for engineering programs. But that same visibility invites noise complaints, aesthetic objections, and complex FAA height clearance requirements. Solar on a rooftop or parking canopy is far less controversial. Permitting is generally fast and straightforward. On space and permitting, wind needs dedicated land and faces a longer, more complex approval process. Solar can go on existing structures and often gets fast-tracked by municipalities. On maintenance, wind needs specialist turbine technicians on an ongoing basis. Solar can be managed by a standard facilities team. On scalability, solar is modular. The university could start with a smaller array and expand in phases. Wind is an all-or-nothing single asset. The honest qualitative picture is that solar wins on nearly every non-financial dimension: easier to build, easier to maintain, less risky to implement, and more flexible. If the NPV numbers are similar, solar would probably be the right call. It's wind's wide financial margin that tips our recommendation. I'll pass it to Jeremy to close us out.
Thanks, Nolan. So looking at question 5, we've got 2 big government programs that really change the math here. First, for wind, there's a federal tax credit that gives us about 2.6 cents for every kilowatt hour we produce in the first 10 years. Since the wind project puts out 6 million kilowatt hours a year, that's an extra $156,000 in value every single year. Over a decade, that adds more than $1 million to an already strong project. Now for solar, we've got the investment tax credit. Basically, the university can deduct 30% of the setup costs right off the top. On a $1.4 million investment, that's a $420,000 discount. It brings our actual cost down to just $980,000, which is great for solar's value and could push its MPV over $1.5 million. Both projects win if grid prices keep going up, but wind wins much more because it's producing so much more power. Plus, we get renewable energy credits for both, and again, wind brings in more of those. No matter how you look at these incentives, both projects look better, but wind is still the clear winner. So, what's our final call? We recommend investing in the wind project. Wind's value, its MPV, is $2.7 million. That's $1.8 million higher than solar. Both projects hit our 8% target, but when you have to choose one over the other, you go with the one that creates the most value. For us, that's wind. The safety net here is also huge. Electricity prices could drop by 37% before this project even starts to break even. Our internal rate of return is 20.6%, which is more than double than what we need it to be. Even with those tax credits helping solar, it still doesn't close the gap. The only reason to pick solar over wind is if we simply don't have the $2.5 million for the upfront cost. If the budget is tight, solar is a great backup. It still creates a ton of value, but if we can afford the investment, wind is the way to go.
I completely agree with Jeremy and everyone else's analysis that wind would be the go-to method for energy. A big thank you to everyone who came today and helped with the case study, and thank you if you are watching the case study.